Bonjour à tous. Je m'appelle Jerson. So I am captain from Brazilian Army, and it's a great opportunity for me to be here and share my work with you. I'll talk about my paper with the title Navigate Decision-Making Frontiers, Virtual Reality and Spatial Skills in Strategic Planning. The authors of that paper are me, the professors Anderson Maciel and Luciana Nedel. To begin, I would like to draw your attention to something you all rely on daily, navigation. Here you can see an example of how can you use Google Maps to navigate through a city, something many of us do without a second thought. And this is made possible by modern technology that provides real-time directions and updates. But if you do not have access to this technology, what can you do? So here you can see a more traditional approach, the roadmaps. And are still essential tools, especially in situations where the digital navigation is not available, such as remote areas, emergencies, or when technology fails. And this brings us to an important point. Despite all the advancements in digital mapping, understand and interpret maps remains important. And this is particularly in fields like military planning, where reliance on technology may not always be possible, and the ability to read and interpret maps could be the difference between the success and failure. And what are the use of maps in military planning? So we need to define the best ways to accomplish the missions, of course, and to do that we need to understand the terrain elements to make the decisions. And during the mission executions, we need to know if we are still following the plannings, and we need to know where our troops are and what's the enemy's directions during the situation warrants to prevent the fraud side, for example. Here you can see of how the ability to use a map and correlate the information with the real world is a difficult that is not easier. So here you can see a real point of view that corresponds to a specific point on that map. So we need to observe the vegetations, the paths, the constructions, the elevations, and correlate that information that we have in the real world with the topographic map. That's not an easy task. You need, of course, to know the difference elements that we have in the map and correlate that information with the real world. So that's means that we have to transform a 2D information in a 3D conceptualization and then do the correlation between both. That's the same ability that we need to use to solve that kind of task here, where we have a determined geometric form like a cube, and we need to mentally represent the complete form after getting all sides and select the correct answer. That means that we have different levels of spatial ability. Some individuals will lead with that with more facility than others with more difficulty. So what could be done to solve that error, that problem? In the military planning, we use the sandbox. That's a manual representation of the terrain and the main elements of the maps, such as hydrography, paths, constructions, using sand. So individual needs to interpret the map and then represent the elements using the sand. So that could be done with errors because it's a manual representation. And the other solution could be the use of the technology, of course, such as augmented reality, virtual reality, and computer vision applications. We see in other studies that immersive environments could offer new perspectives for the users, basically in relation to the geographic data and virtual reality, with an intuitive understanding of the terrain. But there's still a lack of how can such mechanisms could really improve the military planning. So searching for answer that question, we build our own virtual reality application with based in three main principles: terrain, the 3D models and data set, and the interaction. First, the digital terrain. To make it, we use a digital elevation model from Earth Explorer, and we apply as textures topographic maps obtained using the Brazilian Army Geographic dataset and high-resolution satellite images from Google Earth. And we made our digital terrain, as you can see here. And 3D models and dataset, similar to the conventional approach, where the users could select the positions based in the miniatures, we introduce 3D models of the weapons and vehicles, and we associate with that models a way to visualize the range in 3D. So we associate with a spotlight component with the range elements. as you can see here. And finally, the interaction with Storm and Go, because we base the movements in the natural movements, searching for a user-friendly tool. So the user could grab the miniatures, draw on the surface of the map, for example. Here you can see our app working. The user can select the model in a list, and a spot point will appear in front of him. He can grab how many copies they need for the planning, and after that he can destroy the spot point if no longer needed. He can switch between the topographic map or the high resolution satellite images during their plannings, and can resize the element with the real scale. And a sphere will appear to help them during the manipulation process, as you can see here. But of course, after the development, we need to prove how such mechanisms could really impact the military planning. Searching to answer that question, we built a user study, searching for compare the conventional method with the virtual reality application. And we explore the impact on planning and searching for improve the spatial map reading skills, because we aim to mitigate negative effects on lower skill individuals. And our main hypothesis was that VR can quickly remove barriers between them. But of course, first we need to select our target audience. And to do that, we administrate two tests, the topographic maps assessment and Santa Barbara storage test to evaluate maps reading and spatial skills respectively, to a sizable group, primarily comprising by cadets and instructors of our military academy. And a total of 106 participants took this test, enabling us to identify our target for improvement. But we select only 36 participants because we select 12 for each quartile of the results of the preliminary evaluation. So the highest results, the median, and the lowest. And we define different execution orders. Some individuals will start with the conventional method and others with the virtual reality. And to prevent cross-contamination, we have two variants of the main task. So we have maps A and B, for example. And what are the tests? So the users need to select optimal positions for observation posts, and we compare the participant position in both methods, virtual reality and conventional method, grade them from 0 to 10, based on factors aligned with our field manuals. And we explore how individuals use different views, zooming and mood scale, and how they interact with VR during task execution, such as number of movement, object movements, or how they navigate the environment. And what are the results? So here you can see basically a direct correlation between the results of the individuals and the preliminary evaluations. So the red line represents the VR method and the blue represents the conventional method. So we have a direct correlation between the grades obtained by the participants and the spatial abilities, and we see that the influence of the method used, the VR and the conventional, and how the execution order affects the user's ability. So that means that could really improve their grades using our VR application, impacting the lowest individuals positively. And as shown in the graphics, the participants with lower spatial skills tend to move more while completing the tasks, but this did not significantly influence the number of object movements. Interestingly, higher scores were associated with significant greater zone usage, suggesting a more engaged approach to spatial exploration. So in conclusion, you can see that VR can enhance map interpretation and spatial skills, and the VR's potential as a powerful tool in military planning, but we have some limitations, like the small sample size, just participants per map condition pair, that count in the United States the findings, and we have just one individual doing plan evaluations. Of course, in future works, we can expand this with more participants and more plan evaluations, but we see the opportunity to implement that as an education tool to assist the cadets in interpreting challenge maps, as well as a supplementary analysis for real missions support the decision-making process. In future work, we can explore the integration of haptic feedback too. So that's the end. Thank you for your attention. Thank you for your time. If anyone have any questions, feel free to ask.